Okay, so in the previous class, we did second order for the under-damped system and the critically damped system with the X over F for the mass spring damper was Coulomb transfer function was omega n squared S squared plus 2 zeta omega n S plus omega n squared. And we saw that when we apply impulse delta of t x, this was for under-damped system, and this was for, as you saw and we draw it mathematically, for critically damped system. This is for zeta 1 and this is for zeta smaller than 1. And then we saw that if we apply step x and the step as the input, and this is the step, this was for under-damped system and this was for critically damped system, right? Zeta is 1 here and the zeta is smaller than 1. So here we found too many things. One of them was the raise time, that was tan 1 over omega d, 1 over omega d tangent inverse of minus 1 minus zeta squared over zeta. This is the raise time here. And we found the peak time, that was pi over omega d. And we found the overshoot in percentage MP, peak, maximum peak, in percentage was E minus zeta pi over 1 minus zeta squared. And for 5% settling time was 4 over zeta omega n, and for 2% criteria settling time was 3 over zeta omega n. And then we move to ramp t, when the input is the ramp, and the x, we saw that this is ramp, and we have oscillation of here in the transient response, and then steady state error signal, and for the under-damped system there is no oscillation and goes here. And the steady state error signal of here was 2 zeta over omega n, and here ESS obviously was 0, and the ESS was 0, steady state error signal. And finally we did for the parabolic x and t. So this is the input to the system. Again, for under-damped system we have oscillation like this. Actually we did this? No, we didn't, that's right. We didn't this, that's right. So until here. So we had this. Oh yeah, because we did that, I'm sorry. So we had for the parabolic 1 over t squared as the input. So we had inputs like this, and here we had oscillation for the underdamped, and we had no oscillation, and finally it was like. And you saw that the steady state error signal of this, obviously as it shows, increasing with time. Okay, guys, this is the summary of what you have done for the second order system. Now let me go to the last case. I just want to give you the first example because I don't want to waste your time, because I'm going to move to the Simulink. The last case is when your system is overdamp. In the previous cases, as you saw here in summary, you had the underdamp and critically damp. Now we have excessive damping in the system. Being said, I just want to consider when applying impulse, because the f of s is 1. So from here you get x is equal to, and you remember from, if you look at your notes, when you have the overdamped system, the poles of the system, they are distinct real poles. Zeta omega n plus minus omega n zeta square minus 1. Remember, you have this in your notes. I'm just plotting it here. If you plot it in the real and imaginary part, so you have this two real poles side for the overdamped system. So your x is gonna be omega n square s minus p1, because fs is 1, s minus p2, and this equals to a s minus p1 plus b s minus p2. Obviously this is a s minus p2 plus b s minus p1 in s minus p1 s minus p2. From here, because I have done many times in this class, this is equal to omega n square. You can simply get that the coefficient of the s is 0 because we have no s in the numerator here, and minus a p2 minus b p1 is equal to omega n square. From here you get a is equal to minus b, and implement here, it's going to be b p2 minus b p1 is omega n square. So your b going to be omega n square p2 minus p1. Obviously, because these are distinct poles, p2 minus p1 minus zeta omega n plus omega n zeta square minus 1 minus p1 minus zeta omega n minus omega n zeta square minus 1. This is p2 minus p1. This with this goes, and you get 2 omega n zeta square minus 1. So you get b as simply omega n 2 zeta square minus 1. If you implement here, you get b from here. Okay, guys? And you get a as minus b minus omega n zeta square minus 1. And here has a 2. So, can I go to next page? Everybody? Yes? So, x of s gonna be omega n 2 zeta square minus 1 over s minus p2 minus 1 over s minus p1. Just See, because B is positive, I'm going to move it. A is negative, I'm moving it. Okay, so now if you want to find the x of t, just put Laplace inverse. Now you know that the Laplace inverse of this term is the exponential term. You have your notes in the table of oh, what happened? Okay. No, okay. It's recording. Yes. Okay. So x of t for the overdamped system gonna be omega n 2 zeta square minus 1, and here you get e p2 minus zeta omega n plus omega n zeta square minus 1 in t minus e p1 zeta omega n minus omega n zeta square minus 1. That's it in t, obviously. This is the answer for the overdamped system, and you see that there is no oscillation, like as the critically damped is exponential, and the real numbers here, not imaginary, like as critically damped, but the only difference is that here we have two distinct real poles, despite the case of the critically damped that we have repeated real poles. So if you want to plot it all together, here we go. T x, and this is the input to the system impulse. So this is gonna be underdamped system. This is gonna be critically damped system. What's the difference here between critically damped and overdamped system is overdamped system is much slower. I never like this. This is for critically damped system. But there's no oscillation as we had for the underdamped system. And nothing changes. As you see in a steady state phase, the output follows the input. So ESS for the impulse is 0. You can now copy this if you are done. Are we done? Yes, guys? You can copy this when you have a step input. Underdamped, critically damped, and overdamped. Overdamped is slower. But as you see again, steady state is 0. Nothing changes. This is for unit step as input. Now, if I copy this for the ramp, you're gonna see that. If I copy this for the ramp T, I'm skipping the mathematics because it's the same as we did T for the ramp. So obviously you're gonna have this underdamped no oscillation, critically damped, and it's a little slower overdamped. I mean that slower to settle down. And copy this for, finally, parabolic t and x for parabolic. Obviously here is x, here's x. And this is the input. And you have transient for the underdamp, increasing with time. This is no oscillation. And you have a slow response here for overdamp. No oscillation, okay? This is just my hand oscillation. Okay? And in all the cases here that you see ESS gonna be 2 zeta over omega n, and the ESS gonna be infinity when time goes to infinity. Understood? So let's go to Simulink. Guys, can you see me? Yes? Are you here, everybody?
Yeah.
Okay, I thought that my computer is strange. So, because I'm gonna share with you everything I have to do in the Simulink first. And as an assignment, I want that you go and develop everything based on MATLAB code for underdamped, critically damped, and overdamped system and compare together, okay? So what I'm gonna do, I'm gonna open ramp second order system. Okay. Let me pause it. And then I'm gonna save this as okay, Simulink second order comparison. Okay, and obviously I'm gonna go with the ramp and step. I'm gonna tell why. Okay, so second order system gonna be omega n is 5, so it's gonna be 25, and I mean natural frequency 2, and for underdamped system I'm gonna say is 0.2. Omega n is 5, 2 zeta omega n, and 0 because you have to put here what? Open loop transfer function. That's right, remember. Okay, and then obviously here, oops. Okay. Okay, this is for now critically damped system. The previous one, so zeta is 1. Here we go, bingo. And then I'm gonna copy paste this, okay, for overdamped system. So for overdamped system, zeta is greater than 1, so I'm gonna put 2. let's say 3, okay, 2 zeta omega n. Here we go. Okay. And then this I want to compare with underdamped, critical, overdamped system. I'm gonna make the inputs of the marks as 4. I'm gonna push this to be compared with this. This is for, I am writing here, this is for underdamped, this is for critically damped, and this is for overdamped. Okay, and I'm gonna compare the error signals together for the second order system. Here we go. Okay, and save this. So remember that for the coding you have to put the closed loop transfer function, but for the simulating you have to put open loop transfer function. 1, 2, zeta, omega n, and 0 because open loop transfer function. Underdamped, critically damped, and overdamped because zeta is greater than 1. Now I can run this. And if I plot all of them for the ramp input, you see that I can make it big. Okay. This yellow line, guys, what was for underdamped system. This blue is for what? Critically damped system, no oscillation. And this is for overdamped. You see that overdamped takes much longer time to settle down. See what I'm saying? And these are 2 zeta omega. Okay? Because when I'm increasing the zeta, the error signal increases. Right? 2 zeta over omega. The steady state error signal. Now if I want to make it more visible, I'm gonna share with you, I'm gonna decrease the damped natural frequency to a much lower value. Okay, underdamped system, and you're gonna see much more oscillation. I'm gonna make it to 10 seconds. Here we go. See guys, underdamped system, critically damped system, overdamped system. Overdamped system is much slower to settle down. Critically damped system settles down here at 1.2 seconds. Overdamped system, as I told you, takes almost 4 or 5 seconds to settle down. And this is the underdamped system. Clear, everybody? Yes? So I'm not changing everything. I will just copy all of them and move it here. Why? Because I'm gonna just run for the step. Okay. And your step, you have to check that step time is 0, not delayed step. Always do it. Okay. So, and copy paste. Okay, just put it here. Copy paste. Just put it here. Now, if I run that, obviously you're gonna have the step response that is more visible for what I talked. See, unit step, underdamped system. See, critically damped system, no oscillation. As I told you, overdamped system, no oscillation, but takes a much longer time to settle down. Clear, everybody? To make a good vision here, I'm going to increase this underdamp a little more to 0.3, okay, to give you a good picture for us. There we go, see? Bing. The maximum overshoot of this is almost 40% because it is 1.4, here is 1. So it's 40% overshoot. That's too much when it comes to control class. I'm going to teach you how to design a controller that's reduce this to 25 or 20% based on the desire of your boss. And you have raise time of almost 0.4 and the settling time of almost 3.4 seconds. And the peak time is almost 0.7, like that. See, peak time. Everybody understand? Yes? And obviously, as I taught you, the error signal goes to 0 for all of them. For underdamped system goes to 0. For critically damped system goes to 0. For the overdamped system goes to 0. But overdamped system, error signal goes 0 much by taking much more time. Okay? Everybody? Clear? So now, as homework, you do for coding, for both coding and for yourself, and for Simulink for the impulse and parabolic. I taught you how. You have to change the transfer function because in Simulink and MATLAB coding, we don't have impulse and parabolic. You have to change the opponent transfer function. I have done this several times. Go to your notes and see how I have done. Okay, guys? Clear? Yes? Now, being said, let us continue our topic. How? Easy. So, remember that what I have done was for second order system, was for spring, damper, and force as second order system. Now let me model another second order system that equals exactly with this. R L C circuit dynamics is copy of the mass spring damper. They are the same system dynamically. Here is plus minus from high voltage to low voltage, or inductor and the capacitor. And because I promised you that I'm going to show that they are the same system dynamically. So applying the Kirchhoff voltage law, and here's the I current, you get that the Vin equals to voltage of the resistor plus voltage of the inductor plus voltage of the capacitor. Here is voltage of resistor, here is voltage of inductor, and here is voltage of capacitor. But we have only one current inside the circuit. So what I'm going to find closed transfer function of Vc over Vin here. Okay, everybody? So we know that VR is Ri, or resistor, from high school. VL, if you forget it, I'm writing here that the voltage across inductor is L di over dt. Inductance, this is inductance, di over dt. So you're going to have L di over dt. And the Vc, you know, that is 1 over, and Vc is Vc because we're going to find it, Vc. But I taught you in the first order system, if you have in your notes, that Vc is equal to 1 over c integration of I dt. And from here you get I, you have in your notes, is c dvc over dt. What I'm going to do, I'm going to apply this I here and I here. So you see that the Vin, input voltage, gonna be RC dVc over dt plus L C d square Vc second order time derivative plus d in d square plus Vc. Or if you rewrite it, you're gonna have LC d square Vc over dt square plus RC dVc over dt plus Vc is equal to Vin. Okay, guys, can you hear me? Yes? Everybody?
Yes.
Good. So that shows that this is second order system because you have second order time derivative. Being said, we want to go to the Laplace domain. Here we go. By assumption that Vc at time 0, voltage of the capacitor is 0, and the rate of the voltage of the capacitor at time 0 is 0, like as we did here for the massive spring damper. So, being said, you get LCS square VCS. Remember, second time derivative gives you S square. Two derivatives. Plus RCS VCS plus VCS equals to Vn. Or VCS is LCS square plus RCS plus 1 equals to Vn. And the closed loop transfer function gonna be 1 over LCS square plus RCS plus 1. Bear with me, I'm not done. I'm gonna factor out LC from here. You're gonna have 1 S square plus LC, factoring that, plus R over L S, that's right, in 1 over LC. Now I can move this up, equals to 1 over LC S square plus R over L S plus 1 over LC. Have you seen this before, guys? Have you seen this before? Yes, in massive spring damper. So look at the massive spring damper second order system in general. What is this? 1 over LC. What is this? I'm just writing. Look at here, guys, all of you. Here we go. No. Okay, second order system. Look at here. What is L over C? 1 over LC. What is that? What is that? Squared. So naturally you see, oh, your RLC circuit, look at the massive spring damper has natural frequency to oscillate its voltage. So natural frequency of the RLC circuit gonna be 1 over inductor in capacitor. Obviously again in radian per second. Natural frequency is always a radian per second. Bingo. How much is R over L as I showed you? How much is R over L? How much is that? 2 zeta omega n. So 2 zeta omega n is R resistor over inductor. Agree everyone? So from here you get that the damping ratio of the RLC circuit is interesting, right? Is R over 2 L omega n. We have omega n, so zeta is R over 2 L 1 over LC. Right? Or mathematically, if you simplify it, it's gonna be 2 LC. Bingo. So your RLC circuit has a damping ratio. So I just proved you that this is equal to omega n square s square plus 2 zeta omega ns plus omega n square. And I just proved you that RLC circuit is massive spring damper. They have exactly the same dynamics with different parameters, but we converted different parameters to our lovely standard form, zeta and omega. See what I'm saying? Yes, everybody? Why we did this? Because the name of this course is the modeling of physical system. We are trying to find the similarity between the dynamical systems. This dynamical system can be electrical, can be mechanical, can be fluidic, can be electromechanical, can be electromagnetical. That's what I'm going to teach you. And too many things. At the end, they are following, at the end, they are following the same fundamentals. Agree, everybody? So being said, whatever I derived for underdamped, critically damped, for different inputs that I plotted today, also by Simulink, for impulse, for ramp, for parabolic, okay, that I did for the massive spring damper, you have your notes, is valid for our RLC circuits. I don't need to repeat it. And that's for the powerfulness point of this course. When you know that RLC circuit is the massive spring damper, whatever I developed for the transient response, I don't know, the steady state response is exactly the same like that. But the only difference is that when I say the peak time for the for this voltage of the capacitor, Tp that we calculated was pi over omega d. You only have to change the parameters because omega d is omega n. Remember, 1 minus zeta square if your system is underdamped. This. So peak time of the RLC circuit, omega n was like this. 1 over LC 1 minus zeta square. R square over 4 LC. See, your peak time has a different. See that what is affecting on the peak time of the RLC circuit is the inductor, resistor, and the what? And the capacitor. While for the mass spring damper, TP this is the same. This is the same. Going to be pi over omega n. For mass spring damper, omega n is, as I told you, k over m. And what zeta for the mass spring damper was c squared, damping coefficient, in 4 km. See what I'm saying? Everybody? Yes? So in the next class, I'm gonna make the loop complete. I'm gonna say that mass spring damper equals with the RLC circuit, and it equals with the 2 tanks of the water or fluid. 2 tanks of the fluid. I'm gonna make this in the next class. And we officially are done with second order system, and we're gonna move to higher order systems. Okay? Everybody? Any questions? Yeah, obviously. Obviously not in this level of the simple level, but I'm gonna talk with you about the midterm, because midterm is on the first week after your break. That's right. I'm gonna send email, okay, to everyone and say how it is. Actually, we discussed in the beginning of the class.